Now let's talk about some special cases of centripetal acceleration. So first special case we'll talk about are just horizontal circles. So things going around uniform speed in a horizontal circle, like a block at the end of a string sitting on a tabletop and going around in a circle on the tabletop. When we free body diagram this block here, and remember, free body diagrams for objects in uniform circular motion, they're just a snapshot at any particular point. I can take a snapshot as it's drawn here, or I could even, if I wanted to, I could take a snapshot of the block over here. Well, it's drawn very conveniently in this orientation here, so I'll just free body diagram it as it looks right here, at this snapshot right here. So if I free body diagram this, then we have, this is a free body diagram of the block. We have this here, and the forces which act on it. By the way, I'm going to give a coordinate system, but I know that my acceleration, as I free body diagram right here, my acceleration has to be towards the center. And so at this snapshot here, my acceleration is to the left, and this is a centripetal acceleration. So just for convenience, I will make my coordinate system be a positive x off to the left. And I'll have a positive y upwards to stick with traditional coordinates there. So the forces that act on it, clearly there's a weight of the block, there's a mg, and then I have some normal force exerted by the table onto the block, and then I have a string attached to it, right? So there's some tension force here, which I'll just call F. So there's some tension in the string. We'll assume that there's no friction here. There could be a frictional force back off in this direction, helping us to accelerate it that way. But we'll assume that this is a frictionless tabletop, just connected by, so the block is just connected by a string here. So when we do this, it's really just exactly like we've done any other problem involving Newton's laws and forces and free body diagrams. We like to put the acceleration here off on the side, so I know what is the outcome of these two, of all these forces, and then I just have sum of forces in the x direction equals mass times acceleration in the x direction, and then sum of forces in the y direction equals mass times acceleration in the y direction. If we had a frictional force, we might want to do this one first, but we don't. We're going to ignore the frictional force. And so let's just say that, I don't know, I was given a speed. I don't know, let's say we're given, let's say we're given a period, and we're given a radius, and we're given a mass, and we can find this force. Then we'll simply sum our forces in the x direction. Will be mass times acceleration in the x direction, but it's a very particular acceleration in the x direction. I don't need to tell you the acceleration. Instead, I can give you the period and the radius, because this is the centripetal acceleration. So we would get here, calling positive to the left. F is positive, AC is positive, and we just get F is equal to mv squared over r. That's our centripetal acceleration, or this is equal to m times, we said centripetal acceleration is 4 pi squared r over t squared. So given r and t and m, we can just plug in and find this force. So horizontal circles is just means that something is moving around in a circle in a horizontal plane, like on top of a table if it's moving in a horizontal plane. We could also have something like maybe a tether ball. So here we have this pole here in the ground, and then let's say there's a ball attached right here, and let's say that this is going around in a circle. Now it's going around, and this rope has a length of L, okay? And let's say that we know some angle it makes with the vertical, theta here. Actually, let me call this beta so we don't get confused. So this is the angle beta. Let's say we're given some mass. Now this goes around in a circle, and the type of circle it goes around would be a horizontal one. It would be going around a circle like this, right? It's not going off in a circle like where it's going up and down like that. And this is still going around in a horizontal circle. So when we free body diagram this, let's choose a coordinate system here because I drew my mass off to the left. As I take a snapshot, it'll need to have some acceleration off to the right. Will be my centripetal acceleration. So I'm going to make my positive direction off to the right just for convenience. Don't have to, but it's more convenient to do so. So when we free body diagram this, we'll have this ball here. Then we'll have some mg going down like that. And then we have some tension like this, right? Or some ft. This is our tension force. The rope is pulling this direction, right? And then the outcome of these are that we have some acceleration this direction. It's a centripetal acceleration. So now we just have components, right? If it's moving around, at the top of this pole, but it's moving in a horizontal circle, it's only accelerating in a horizontal plane. It's not accelerating in a vertical plane. It's not accelerating in the y direction. It's only accelerating in the x direction. So we would say that we have some y component here. Call this fy. There's also some x component here, fx. And when we sum these forces, we'll get, these must balance out since the acceleration in y is 0. The acceleration in the y direction is equal to 0. It means that we're going to have fy is equal to mg, and acceleration in the x direction is equal to mass times the the acceleration in the x direction is the centripetal acceleration. So this means that fx is going to be equal to mac, which is equal to mv squared over r. And so then we can just solve this system. I won't do it here to save time in the video, but we just have the system here which we can solve. One important thing to note in a horizontal circle like this, though, is that the r in the magnitude of your centripetal acceleration is not the length of the rope necessarily. It is the radius of the circle, not necessarily the length of the rope. So the r here would be this. This would be r. And which, if I have, this is beta, r is going to be equal to, this is L, this is beta, this is going to be L sine of beta. So not necessarily just the length of the rope. If it were going around a circle like this, then yes, it'd be the length of the rope, where I go to a distance L out here as well. But that's not the type of circle that it is going around. And the radius of the circle would be this, which is the length of the rope, times the sine of beta would be the length here. So just one thing to be careful with on that. So then we have a system which we can solve for that for horizontal circles.